For you.
Uh-huh.
Tomorrow's session at 6 o'clock.
Right.
Can I switch that to a half-hour session?
Absolutely. You can always do that. Even you could have waited and done it tomorrow night.
Okay.
I'll switch it to a half-hour session right now, but I never have any problem with that. In other words, if
Oh,
you schedule an hour session and at the end of a half hour you're done with all your material, you're ready to be done, you can say something and that's fine with me.
okay, great. Thank you.
Okay, so I've done that. And what do we got going tonight?
Um, I just wanted some practice on graphs.
Okay,
So
so this is,
this first,
go ahead.
this first one, the directions are use transformations to graph each function. Determine the domain, range, and horizontal asymptote of each function.
Okay,
So the first one is f of x equals e to the negative x plus 5
in the exponent or on the,
on the algebra line.
okay, like that.
Yes.
All right, so if we're trying to figure out the transformations, we need to figure out what the parent function is. So what's the parent function, which we will call g of x?
E to the power of x.
Uh-huh. And let's graph that. Looks like most exponential functions. Can't tell a whole lot other than you know that point. What's that point?
0, comma 1.
All right. Now, the way I think the only way you can really figure out these transformations is to try to figure out how to write this function in terms of g of x. In other words, if I said, what is g of x plus 5? What would that be?
F of x. Or, sorry, not f.
No, that would be e to the x plus 5, right? In other words, that would be my g of x function plus 5, which is not f of x. So how would I figure out what f of x is in terms of g of x?
G of negative x.
There you go. That's what you want, is to be able to write it like this. Now that's f of x. And based on this, you can tell everything that's being done. What's the consequences of the negative x inside the parentheses?
A reflection over the y-axis.
So let's do that first in green. Always do your reflections first, always, both vertical and horizontal. I call a vertical reflection a reflection over the x-axis. Okay, and the second thing that's being done?
A vertical transformation is positive 5.
Vertical shift up. Up 5. Because there's horizontal shifts also. So you have to distinguish between a vertical and a horizontal shift, and you have to say which way. So to do a vertical shift of this green line, I would merely take this point that's at 0, comma 1 and move it up 5 units. So it's now 0, comma 6. And draw the curve basically parallel to the green curve. What's the new horizontal, well, what was the old horizontal asymptote? What was the horizontal asymptote for g of x?
Y equals 1.
No, actually y equals 0. In other words, look at the black line. It is approaching the x-axis. If I continue on to negative infinity, this thing will get closer and closer to the x-axis. Well, the equation of the x-axis is y equals 0.
Right.
So I'm moving my horizontal asymptote up 5 units. You said x equal 1 or y equal 1, didn't you?
Yes, I did.
You were correct. Sorry, my mistake. In other words, no, sorry.
Yeah.
No, been a long day. My original asymptote for my black line was y equals 0, and I've shifted it up 5 units. So for my red line, the asymptote has to be y equal 5. And I can see that if I draw it. You see why the horizontal asymptote has to be y equal 5?
Yes.
Okay. Now let's talk about domain and range. Perhaps the first thing I should do is erase the lines that don't matter, and let's look at our red graph. What's the domain of that?
All real numbers.
Correct, and you can determine that algebraically also. In other words,
Right.
If we look at f of x, we can tell that there is no value of x that we can't have. We can let x be equal negative infinity, we can have it be positive infinity, we can have it be 0. In other words, there's no restrictions on the domain. But if I look at my graph, what's the range?
5 to infinity.
So in interval notation, the range is 5 to infinity, and should that left thing be a parentheses or a bracket?
Parenthesis.
Because it can never be 5.
Correct.
For this function's value to be 5, I would have to somehow figure out how to make that equal 0, and you can't do it. There's no value of x that makes e to the minus x equal 0. And you can also tell by looking at the graph. So all of these questions you can answer algebraically by looking at the function, but it's almost easier to answer domain, range, and asymptotes by looking at the graph, and since they've asked you to graph it anyway, probably the best way to handle these problems is to graph it first, then check your domain and range and make sure that it's right. And in fact, that's why I knew that y equal 1 wasn't right.
Right.
Because I looked at the graph and I could tell that that horizontal asymptote was a lot higher up than 1. And then, of course, algebraically, if you figure it out, you figure it has to be up 5. Vertical shifts basically change all the horizontal asymptotes up by however amount of the shift.
Right.
All right, so what else?
So same exact direction, same kind of problem, just f of x equals negative e to the power of x over 2, all plus 2.
So again, our parent function is e to the x. Now, how would I write f of x in terms of a transformation of g of x?
Negative g of x.
Not quite. negative g of x over 2.
Oh, right.
In other words, whatever that thing is there, that has to go in the parentheses,
Right.
plus 2, outside the function. Here's the way I tend to think of transformations. Let's talk about this, because I can tell you're good at transformations. But you have 3 vertical transformations and 3 horizontal transformations. Okay? You have vertical reflection, which is minus f of x. I didn't need that other parenthesis. You have vertical shift, which is f of x plus some number. You have vertical stretch and shrink, which is some number times f of x. With me?
Yes.
And then you have 3 horizontals. Horizontal reflection is f of negative x. Horizontal shift is f of x minus some c. And a horizontal stretch, actually the horizontal, we should say shrink slash stretch, and that's f of some c times x. Notice the difference between verticals and horizontals. Verticals, everything is outside the function, right?
Right.
Horizontals, everything is inside the parentheses or inside the function. And that's the way you want to look at these. So when we were looking at our last problem, we can see that this x over 2 has to be inside the function. It has to be inside the parentheses. The minus is outside the function. So it goes there, not up there. If that would have been a minus x over 2, well, then the minus sign would have to go inside the parentheses.
Right.
Okay. What else? Did we answer everything on that? I don't think we did.
No.
Not even close. Yeah, we didn't finish the problem. So the first thing you want to do is what?
Graph the parent function.
Okay, which we've done in black. So the next thing you want to do, because order matters only when you have reflections involved. If
Right.
you have reflections involved, then it's very important that you do the reflections first, not second. And if you have 2 reflections involved, it doesn't matter which order you do them in, just do both reflections before you do anything else.
Okay.
So the first thing I want to do is the reflection. I'll do that in blue. And I'm reflecting over which axis?
The y-axis.
No, this is a vertical reflection. A vertical reflection means you're flipping over the x-axis.
Okay.
You see why I call that a vertical reflection?
Yes.
Yeah, and rather than a reflection over the x-axis, because it matches all of the other vertical transformations. It's outside the function.
Right.
Now, inside the function is, what would that be? What kind of a transformation would that be?
Would what be?
The x over 2.
It's the same as x times 1/2.
Okay, you're right. So I could have written this as minus g of 1/2 x, which,
So
what's the consequences of that 1/2?
it's a vertical shrink.
It's inside the function, right?
Right.
That means it's horizontal.
Okay.
Everything inside the function is horizontal. Everything outside the function is vertical. This negative sign is outside, that's vertical. This +2 is outside, that's vertical. This 1/2 x is inside, that's horizontal. Now, is it a shrink or a stretch?
Shrink.
By a factor of 2.
Right.
And it's opposite of the way a vertical. If I had the following, if I had 2 g of x, is that a shrink or a stretch?
Stretch.
Right, because 2 is greater than 1. In other words, when you're outside the function, the size of this number determines whether it's a stretch or a shrink. Anything between 0 and 1 is a shrink. Anything greater than 1 is a stretch. And it's exactly the opposite when you're talking horizontal stretches and shrinks. When the number is greater than 1, it's actually a shrink. When it's less than 1, it's a stretch. Okay? You with me? So if I draw the consequences of that 1/2 x, I know that that is a stretch, and a stretch manifests itself that way. In other words, I'm stretching it horizontally.
Okay.
Okay? And I'm stretching it because this number is between 0 and 1, as opposed to vertical stretches where it has to be greater than 1. So just know that the vertical and the horizontal kind of act opposite of one another.
Okay. Mr. Cowan, can you go back to what you said just a minute ago? Something about, for vertical, a stretch is actually a shrink, or?
Yeah. Let's take a different function for a moment. Yeah, hopefully you can get back to this page. Let's take f of x equals x squared. Okay. Well, that's what that function looks like.
Right.
If I did a vertical stretch outside the function to f of x, that is a stretch. That is going to make that thing skinnier.
Right.
Because every point that was on the lower green line is now twice as far away from the x-axis, right? In other words, if I had a point right there, it's now up there. My point right there is now up there. In other words, it's 2 f of x, not just f of x. And the effect of that is you end up with a skinnier parabola.
Okay.
Whereas if I had 1/2 f of x, that is a vertical shrink. Notice that every point is half of the other green line, the lower green line.
Right.
Okay? So that's a shrink. So numbers greater than 1 are stretches, numbers less than 1 are shrinks. Now, let's talk about what is f of 2x. Well, I'm inside the function, so it's a horizontal transformation. The only question is it a stretch or a shrink?
Shrink.
Yeah, and a shrink has the same effect as the stretch, the vertical stretch would have. In other words, I'm taking this original green line and I'm shrinking it horizontally. The same thing, you know, I'm pushing it in directions this way. That's what a horizontal shrink is.
Gotcha.
Okay. So
Is that the same equation as 2f of x?
not quite. Notice the 2f of x is 2x squared, whereas f of 2x is actually 2x quantity squared, which ends up being 4x squared. So the horizontal shrink was actually twice as much as the vertical stretch. I didn't really draw it correctly. Let me go back and draw this better. In fact, well, no, I'll draw it like that. It's really twice as skinny as the vertical stretch was.
Okay.
In other words, the horizontal shrink caused the graph to be twice as skinny as the vertical stretch by the same factors.
Okay.
Remember what we do when we take f of 2x is we substitute 2x for x in the parent function. So now we square all of it, and it becomes 4x squared, as opposed to 2f of x, which becomes 2x squared. But that's not as important as remembering that when you're inside the parentheses, numbers greater than 1 are shrinks horizontally. Numbers between 0 and 1 are stretches. So if I had, let me use, I ran out of colors, didn't I? Here, let's see if I can find a better color. Let's use brown. If I had f of 1/2 x, that is a stretch because it's between 0 and 1. And if I plug it in to this, that means really saying 1/4 x squared is what that is going to equal. And 1/4 x squared is like that. Notice that we have horizontally stretched it.
Right.
I've pulled it. It's as if I had, if this was made of string, it's as if I pulled the string in that direction. That's a horizontal stretch.
Right.
All right. So try to go back. Didn't quite finish this problem. So we figured out that the first transformation was a reflection over the x-axis. The second transformation was a vertical, or excuse me, a horizontal stretch. That's the green line. You see why the green line is a stretch, not a shrink?
Yeah.
Excuse me. What? Wow.
Fine. Wow.
I know. Wow. Must be something here I'm allergic. Yeah, if I were to take the blue line and shrink it horizontally, it would look more like that.
Right.
So the green line stretches it out. And then finally, the last thing we're doing is adding 2, which is what?
Sorry. Vertical shift up.
Up by 2. So basically that. What are the coordinates of this point right there?
1, 0. Or sorry, 0, 1.
Yeah, oddly enough, it's the same point as our original parent function went through. Because when we reflected the black line to the blue line's coordinates were 0, comma, -1. Then when we moved that up 2 units, we got the 0, comma, 1 again. So oddly enough, our transformed function goes through the same point as our parent function did. It's fine, it doesn't look the same. But this is also a good spot to show you why it matters what order you do it in.
Yeah.
Let's do it in the other order. In other words, if I move it up 2 first, then I get that, right? And that point is 0, comma, 3. Then if I reflect it, I'm way down there at 0, comma, -3.
Right.
Then if I stretch that, it makes it look like that, but that's not where my final function was supposed to be. Remember what our final function did, and it did this. That's where it's supposed to be. So when you have a vertical reflection and a vertical shift, it matters which order you do them in. You don't get the same graph if you don't do them in the correct order. Same thing with horizontals. If I have a horizontal shift and a horizontal reflection, it matters which order I do them in. If I have a vertical reflection and just a horizontal shift, then I could do them in whatever order I want. It won't change things. But the easiest way to remember it is just always do any reflections first.
Okay.
And everything else after. What next?
All right. F of x equals the natural log of x plus 4. The 4 being in the parentheses.
Okay, good. Parent function. What?
Natural log of x.
Let's graph that. These always go through this point 1, comma, 0, regardless of the base of the log.
Right.
So how could I write this in terms of g of x? What would it be?
G of x plus 4.
Yeah. So g of x plus 4 equals f of x. And now we want to turn our analysis to that. What transformation is going on?
A horizontal shift to the left.
By 4 units. So
yes.
The only thing I have to do is take this point right there, shift it 4 to the left, becomes -3, comma, 0, and draw something that looks relatively parallel to the original curve. Actually, that's a term I invented. Parallel curved lines. I've never heard that in a math book. I think you know what I mean, don't you?
Yeah, I do.
How come I've never heard it? Not sure they're exactly parallel. In other words, I'm not sure that the distance between there is the same as the distance between there. And that's what it would require for them to be parallel. But I tend to think of it as parallel, even though I don't think they are specifically parallel.
Yeah, it's intuitive.
Yeah, it is. But, you know, when you have concentric circles, I've never heard a math book refer to these lines as being parallel to one another. But they kind of
Right.
are, right?
Yeah.
Because that distance is the same everywhere around, then the middle black line is parallel to the original circle and the outer circle. But I've never heard math use the word parallel when talking about curved lines, only straight lines. That's why I say it's my terminology. I'm not sure I'd want you to use that terminology to a math professor. He might say, what the heck does that mean? But you're right, it is intuitive. Everybody would probably know what you were talking about. All right, what else?
F of x equals the natural log of x plus 2, not in the parentheses.
So again, g of x is natural log of x. What's happening to this function? Now you don't always need to go through that analysis of describing it in terms of g of x. Simple ones like this, you can see that the plus 2 is outside the function. That makes it what? Either, is it horizontal or vertical?
Vertical.
Correct. Whereas the other one was natural log of x plus 4, that's inside the function. That's going to be horizontal. So that's all you really need to figure out is whether you're outside the function or inside the function. The only ones that are really tough are things like this. Well, in fact, let's talk about that. You know this stuff pretty good. I'm going to challenge you a little bit.
Okay.
Look at this function. Let me just start from scratch. I'm going to give you a harder one. What is that?
It's the same as e to the power of negative x plus 2.
Good. Now, what is that in terms of transformation?
Is a reflection over the y-axis.
Good.
And a horizontal shift to the left.
By 2 units, correct. Very good. You must have dealt with this already. Because that's probably the toughest there is to figure out, is the one I just gave you. Because you have to, in other words, I can see there's a negative x there, so it would be tempting to write that without parentheses and write it negative x plus 2, and then think that it was a shift. Hold on. No, I did it wrong. I'm glad I mentioned that. That's not the same thing. What do I have to put inside the parentheses to make it what we started with?
You have to distribute the negative?
Well, I got to make sure that it is a negative.
Right.
That's the same thing. That's what makes this problem hard.
Oh, right, okay.
Okay? In other words, that is the same thing as that. But the consequences are different because now this is a reflection over the y-axis, but it's a shift to the right of 2 units, not left.
Okay.
Okay? And you can end up with the same thing as if you did this, 2 minus x. Well, you have to make that same adjustment. That is basically the natural log of minus x plus 2. And then the minus sign represents the reflection, and the plus 2 represents a shift left of 2.
Okay.
So these are easily the hardest ones you're going to run into. And you may, in fact, have some like this in your list that we just haven't gotten to yet. I don't know. Go ahead. Continue with your list.
Yeah, there is one, actually.
Okay.
It is natural log of 4 minus x. Or sorry, f of x equals natural log of 4 minus x.
Yeah, and this wouldn't be, in other words, we know the parent function is natural log of x, but how do I write this in terms of g of x? It's g of 4 minus x, but that doesn't help. Tell me what it is. In other words, it's much better if I can write it like this.
Right. X minus 4.
With double parentheses. In other words, it's only when you get this negative sign in front of the argument, basically, that you know that it is a horizontal reflection. I can't really tell that it's a horizontal reflection from that, or
Right.
what the reflection amount would be. But once I put it in this terminology or representation, then I know I have a horizontal reflection and I have a shift left of 4. Now,
Right.
there is an excellent way to check that when you're doing these. And let's do that. In other words, you can always check to see whether you're right by plugging in numbers. So what I'm saying here is that, okay, my reflection is done first. So in green, I'm going to reflect it horizontally. And then I'm going to shift it in red 4 units to the left, right? Well,
Right.
that point is minus 1 comma 0. Then I got to go through the point minus 5 comma 0. And my curve is going to look like that. Now,
Right.
we check whether this curve is proper or not. Where's the vertical asymptote on that curve?
X equals negative 4.
Yeah, right there. So let's go up and plug x equal 4, negative 4. Ooh. Hold on. I've screwed this up somehow. Let's see. I reflected it horizontally to the green. And then I shifted that 4 to the left, which would correspond to the plus 4. But that should mean that when I make x equal to minus 4, I'm taking the log of 0, and I don't get that. I'm taking the log of 8. So I did something wrong. It makes me think that I'm wrong in my logic here, but I don't, wow. In other words, based on that, our vertical asymptote has to be at x equal 4. Because you cannot take the log of 0.
Right.
So I know that in the end, I need a vertical asymptote right there. And my graph has got to look something like that. So where did I go wrong? Well, I don't know that the graph has to necessarily look like that, but it has to approach the vertical asymptote. In other words,
Right.
the reflection would make it look perhaps like that, but it looks like what I did wrong was shifted in the wrong direction horizontally,
Yeah.
which has to be the case. And yet, let's see, if I expand that, I get minus x minus 4. Well, that's the problem right there. There's my math error.
Okay.
This is not the same as this. That's the same as that.
Hmm?
See why? Distribute that, what do you get?
X plus 4. Oh, okay, gotcha.
Well, you get minus x plus
Plus
4,
4.
which is the same
Right.
as 4 minus x. And that's what
Okay.
you have to make sure you do, is never change it. As much as I preach it, I still make that mistake myself sometimes. So, in other words, this 4 minus x is the same as minus quantity x minus 4, which means that my shift is 4 units to the right. So I'm going to take this point here, shift it 4 units to the right, so that it now becomes 3 comma 0 and becomes asymptotic to the line x equal 4. Now hold on.
Right.
Excuse me, I drew it right the first time, I just forgot.
Right.
Confusing myself here. This line right there, in other words, our final curve needs to have this shape, only shifted to the right by 4 units.
Right. And that point is 3 comma 0.
Yeah. So this final red curve is what we're looking at.
Okay.
But notice how I caught my error. I picked a perfect problem to catch my error, because now to verify that this curved red line is the right graph, well, let's plug in some numbers. If I plug in 3, what do I get? I get the natural log of 1, which we know to be 0. So 3 comma 0 should be on our curve, and it is. And that kind of is verification that I've done it correctly. And whereas the first time when I made the mistake and drew it over here, I couldn't verify the point. When I plugged in minus 4 for x, I got the natural log of 8, not 0. So by testing a point, I caught my mistake. And it's an easy mistake to make. Notice that to go from here to here, most people are going to make the mistake and call that x plus 4. Just
Right.
like I did and just like you did. You have to be very careful once you put parentheses around something that you haven't really changed the expression. That's the key. It doesn't matter whether you're grouping cubic functions or doing transformations of log functions. We've done grouping of cubic functions, right?
I think so.
Well, here's the principle that I'm talking about. there's a cubic function that if I want to find the zeros of it, I'm going to group it. And I can group it because the ratio of 1 over minus 2 is the same as the ratio of minus 1 over plus 2. Right? In other words, the ratio of the coefficients is minus 1/2 there, and it's minus 1/2 there. That means I can group it. But here's the problem. I can't just add parentheses like this. The moment I do that, I've changed it. No longer the same expression. If I want it to be the same expression, I have to change that to a minus sign. Now it's the same expression. Now if I remove my parentheses, it becomes minus x plus 2, what I started with.
Right.
So it's a similar problem as what we were just dealing with. When I want to switch the order of the terms, or if I want to add parentheses, I got to make sure I don't change it. And a lot of times what that means is changing that sign. Whenever this is a negative, then you're always changing that sign right there. The same way that whenever you're changing the 4 minus x such that you can put the negative sign outside the parentheses, you have to make sure that that remains 4 minus x. And it does only if you change the sign on the 4, which was plus, and is now minus.
Right.
So it's a very similar situation. And the answer really lies in always checking to make sure you have not changed the expression. Had I done that, I would never have made that mistake, because now if I distribute that minus sign, I get minus x minus 4, which is not at all the same as 4 minus x. So I know that I've changed it. If I don't want to change it, then I got to change that sign to a negative sign. Basically,
Right.
you can think of, you factored a minus 1 out. In other words, you wrote this expression as minus x plus 4, and then you factored a minus 1 out so that you have x minus 4, like that. I doubt that you'll see anything tougher than that. And I mean, you might see functions that have all 6 transformations. In other words, I could give you a function like this, minus e to the minus x over 3 minus 4 plus 5. Now let's put a number in front too. Minus 6. Now I have, I believe, all 6 transformations. I have a vertical reflection, I have a horizontal reflection, I have a vertical shift, I have a horizontal shift, I have a vertical stretch, and I have a horizontal shrink. Excuse me. The 1/3 makes it a shrink.
Right.
And e to the x is one of the few functions where you can see each of the 6 transformations one step at a time. As opposed to if I'm looking at the function x squared, well, f of minus x is still x squared. Doesn't change. Whereas
Right.
e to the x, f of minus x becomes e to the minus x, which looks different. So each of the transformations when you're dealing with the e to the x function looks different. Whereas when you're dealing with linear functions or even quadratics, you don't see the difference between f of x and f of minus x. So if I'm trying to teach somebody transformations, my favorite function to use is e to the x, because I can show you all 6 transformations and how they change the graph one at a time. Whereas if my function is x squared, f of minus x looks exactly the same. So I can't really show you how it changes it.
Right.
All right, what else do you have? We got another 10 minutes here.
So this is just
Start
solving
from the bottom up if you want. In other words, that one you just gave me, you probably looked, that was near the end of your problems?
Yeah, that one was.
Yeah, because it was the hardest one. So
Yeah.
since we only have 10 minutes, why don't we back up from that point and give me the next hardest one?
All right. Well, now I have solving problems.
Okay.
Just solve for x.
Okay.
Yeah, that's a good one. Log base 5 of x squared plus x plus 4 equals 2.
Okay. How are we going to solve this? It's a log function, so how do we solve it?
Turn it into an exponential.
You got it. What's my exponential function?
5 squared equals x squared plus x plus 4.
Now it's a simple quadratic.
Right.
Okay, I'll let you finish solving it.
So square 5
Okay.
and make it 25, and then subtract 25 from both sides.
Which leaves 0 on the left.
And x squared plus x minus 21 on the other side.
Okay.
And then...
Can we factor that? No, we cannot. In other words, if you look at the factors of 21, let's do it the way I like to teach people how to factor a number. If I start with that, I cannot cut 21 in half. So can I cut it in thirds? Yes. Which means I have to triple the 1. That's the only 2 factors there are for 21. I cannot cut 7 by anything. I can't cut it in half, I can't cut it in a third, I can't cut it in a fifth. So there's no more factors. So looking at this set of factors over here, I need 2 factors that subtract to the number 1. Well, none of these do. So what does that tell me? Where does the solution lie?
The quadratic formula.
Okay, so what is the quadratic formula? What's the general?
Negative b plus or minus the square root of b minus 4ac.
Close. B squared minus 4ac.
All over 2a. Correct? Okay.
Yeah. Have you ever been taught to find the x coordinate of the vertex by minus b over 2a?
Find the what?
If I gave you a quadratic and I said find out where the vertex of that parabola is, let's say I tell you y equals x squared plus 3, and I want the vertex. Let's make it x squared plus 3x minus 2. Okay? If I want the vertex of that parabola, the quickest way to get it is to use minus b over 2a, which would be minus 3 over 2. There's the x-coordinate of the vertex, instantly, almost.
Okay.
Okay? Not everybody gets taught this because there's other ways to find the vertex. In other words, I can put this thing in vertex format by completing the square and then I'll know what the h and the k are my vertex. But if you don't want to go through that process, the quickest way to get the axis of symmetry, or the x-coordinate, is minus b over 2a. Well, notice the quadratic formula, the first half of it is minus b over 2a.
Oh, okay.
Okay? So the only reason I mention it is that if you know the quadratic formula, it helps you remember minus b over 2a is the x-coordinate of the vertex. Or if you know how to find the x-coordinate of the vertex, it helps you memorize the quadratic formula.
Okay.
Also, in the quadratic formula, you were not quite sure what that was.
Yeah.
That actually has its own name. That's called the discriminant. And there's a reason they give it its own name.
If it's positive, then something. I don't
You have
remember.
real solutions.
Right.
If it's negative, you're going to be taking the square root of a negative number, and you're only going to have imaginary solutions.
Right.
And if it's exactly 0, you're going to have exactly one real solution. So if you give me a quadratic and I have to figure out whether there's real solutions or imaginary solutions, the quickest way I can do it is by examining the discriminant immediately, by figuring out what b squared minus 4ac is. Not including the radical, just the b squared minus 4ac. So, and a lot of times it is useful to know whether or not you have real or imaginary solutions. Especially if you're breaking down a quartic or a cubic, get down to a linear factor and a quadratic, you'd like to know whether that quadratic is an irreducible quadratic or not.
Right.
The way you determine that is by examining the discriminant immediately. That will tell you whether or not it's irreducible or reducible. If it's reducible, you want to keep factoring it. If it's irreducible, you leave it as an irreducible quadratic. So there are lots of situations where the very first step is to examine the discriminant. That's why it has its own name.
Okay.
So one way to remember the quadratic formula is the first half of it is the way you would get the x-coordinate of the vertex, and then you have plus or minus the square root of the discriminant. And that's the way I remember.
Okay.
I know in some schools they teach you a little song to remember. Did they ever teach you that song?
No.
No, they didn't me either. But I know the value of songs. I still know my ABCs only if I sing them. You ask me which came first, H or I might have to go A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, and figure out which came first. In other words, without the song, I'm not sure I could actually list every letter in proper order. So those songs can have a lot of value. And I had numerous students that they were taught a song as to how to memorize the quadratic formula. You definitely want to memorize it. That's not something you want to forget. You're not going to just need it this year. You're going to need it next year and probably the year after that.
Right.
And you needed it last year. So it's one of those things that it's extremely hard to memorize, but it's worth memorizing. All right, William. Good place to stop. And
Yeah.
I will talk to you tomorrow night at 6 for a half-hour session. Do I have my
Great.
time right? Yeah, 6 o'clock.
Yes.
All right. You have a good
Thank you very much.
evening.
You too.
Bye-bye.